Hello, everyone. Thanks very much giving the time to present my current research. And today I would like to share my research towards reliable deep learning systems regarding the efficiency, privacy, and security. Okay, before that, please let me briefly introduce myself. My current research interests include deep learning on the computer vision or natural language processing applications. I also do some research regarding the privacy and security, especially about the deep learning privacy and security. And for the computer system and the architectures, I usually try to design some hardware accelerations for the deep learning and privacy preserving deep learning. Okay, so the selected publications show that I have published 11 publications on the CS rankings. And for example, like trustworthy deep learning, I have published like NeurIPS, CCS, ICLR, ICML, DAC, etc. For efficient systems and machine learning, I also published papers on the computer architecture ladder, ICCAD, DATE, etc. And for the teaching, now I'm teaching CDA 5106. It's about advanced computer architecture. And the next spring, I would like to teach the machine learning. So yeah, that's my brief introduction. So let's move to the research overview. For example, I would like to cover 3 aspects. The first one is the efficiency, the second one is privacy, and then security. So why does efficiency matter? Because current AI models are larger and larger. For example, like GPT-2, GPT-3, these models are very large. So for example, they have a large model size, they have a lot of floating point operation numbers, and the latency and energy are very large. So it's important to reduce the model size and the computation complexity. So our solution, for example, is like we design a new transformer architecture and the model compression or the software hardware co-design for that. So for example, our solution show that we can achieve, for example, more than 10 times model size reduction and 5 times float point operation number decrease and almost 3 times latency energy decrease. Okay, this is about efficiency. For privacy, and for example, the current AI models are more data-driven. It means that without data, you cannot train the model. Usually, data is coming from a lot of parties, and so there is a privacy issue. For example, let's see a threat model, the AI on cloud as a service. It requires user data. It might be private or confidential. So it's important to protect the data privacy of users. So our solution is like we design some efficient privacy preserving AI on encrypted data without decryption. And the solution showed that the data privacy user is protected and the computational overhead is significantly reduced. Okay, let's move to the security part. And I'm exploring this part is about the adversarial or the backdoor attacks on the machine learning model. So for example, we try to design a backdoor insertion on the current vision or language transformers. It's a preprint under review paper. Okay, so let me introduce an example of my current efficient deep learning research. It's called Light MTTR. It was published on the on the CVPR 2022. For example, this light MTTR, it's a lightweight transformer for multimodal understanding. And the method is called a dictionary lookup transformer, DLT layer. If we look at this left figure, we can see it's a prior multimodal understanding. And for example, given an image, given one sentence, and the model including 3 components like vision encoder, text encoder, and multimodal transformer. Using this model, it can detect the object conditional on the test. For example, if the test is the man in the red shirt carrying baseball bats, so the model only generate a yellow box on this object conditional on this test. So it's very important application, for the smart TV and these applications. So it's very important. However, it's hard to deploy this multimodal understanding on the mobile devices. So, like red figure shows, we have introduced a method called light MTTR. MTTR is a private work, but for our work, we try to reduce the model size from the 450 megabytes to the 255 megabytes. And using the quantization, we can further reduce the model size to 131 megabytes. So this is the effect of model size compression. Okay, so the problem. So why this problem is challenging is that for multimodal transformers like MTTR, it suffers from large parameters. So model size is big, so it's hard to deploy on the resource limited hardware like mobile devices, personal devices, and the training cost is huge. So for example, it requires more than 5,000 NVIDIA V100 GPU hours to train this model. So for the popular compression method like distillation, new architecture, they require retraining. It's very expensive. We don't want it. And for the compression without retraining, the accuracy will significantly decrease, like factorization, SVD, right? So given a pre-trained model, the problem is given a pre-trained model, how to design its lightweight version. And we have two requirements. The first requirement is how to keep a good trade-off between accuracy and model size. The second requirement is that we do not want the expensive retraining. So given on this problem, we designed the light MTTR. So first, we use the tiny version encoder. It's like a very efficient CNN. And then we design a dictionary lookup-based task transformer and multimodal transformer. So the dictionary lookup is very simple. If you look at the figure A and figure B, you can see for the linear transform layer used in the previous works, and we only use the dictionary lookup transform layer to replace that. So using this dictionary lookup transform layer has two sublayers. The first sublayer is called a dictionary. The second is called a lookup and projection. So if you compare this linear transformer and dictionary, you will see we can reduce the model size and speed up the execution. So our results show that our work retains better performance with fewer parameters. And compared to the half MTTR and SVD MTTR, half MTTR means that we directly reduce the layers of the MTTR. SVD MTTR means that we use the previous method like factorization to design an efficient one. So we can compare that. The light MTTR has a fewer model size. So it achieves comparable performance with the lightweight model. And we also show that the light MTTR can be generalized to different tasks. Okay, so this is about the efficiency. And my research also focuses on the privacy. So let's first look at the, for example, the why do we need a privacy-preserving deep learning? Let's look at the threat model of deep learning services. So assume we have two parties, and the first party is the patient A, the second party is the untrusted server B. So the server B can provide the deep learning services to the patient A, and if the patient A cares about the data privacy, but he has to submit this, for example, the medical image to the servers. Otherwise, this patient A cannot get the service from the server without sharing the data. So if the data is shared, you can see the patient data and results are exposed to the untrusted server. So that's a privacy issue. And this reason why we need a privacy-preserving deep learning. And for the how to support private deep learning, we can use some privacy-enhancing techniques like FHE and MPC. For example, if we look at the threat model, if we use FHE to encrypt the input data, and the encrypted data is shared with the server B. So the server B uses the encoding for the deep learning model, and the encoded deep learning model can directly execute the encrypted data without decryption, and the result is also encrypted. So the server B does not know anything about the data and the result. So it's a privacy preserving deep learning, right? So using this way, we can see the input and output privacy are protected. So yeah, the FHE and the PC are very expensive to compute. So my contributions are trying to reduce the computational overhead of HE-based neural networks. For example, we can design some deep learning friendly FHE techniques, and we can also design, for example, some FHE friendly deep learning neural networks. And in this way, we can achieve efficient private deep learning. So for the future works and the collaborations, I would like to highlight that I still focus on the deep learning, including efficiency, privacy, and security. And I'm very happy to find the collaboration opportunities with the researchers. Yeah, like I also trying to explore the zero knowledge proof, machine learning backdoor, model inversion attacks, etc. Yeah, that's I think that's all my talk, and I'm ready to pick up any questions. Yeah.